Perhaps you've seen the movie The Martian. If not, here's a quick summary. In the near future, a NASA crew explores Mars. During an emergency evacuation caused by a massive sandstorm, one crew member is left behind, presumed dead. Spoiler, he survives. The story revolves around his fight to stay alive on a hostile planet and the challenges of communication with Earth and his crew, who are already on their way back. One of the film's key problems is communication. The delay between Earth and Mars makes real-time coordination impossible. Today, I want to explore this very issue, how such communication challenges could be addressed through innovative technologies like edge computing. Hello and welcome everybody, my name is Florian Kaleitner and today I want to give you a presentation about edge computing on Mars, a form of space edge computing. This means integrating computation and artificial intelligence capabilities directly within spacecraft or satellite systems. First, a short overview. After a short introduction into the topic, I want to explain to you two possible constellations of satellites. Following, the advantages of edge computing on Mars. After this, what the status of edge computing on Mars is. Afterwards, what other possibilities there are to provide edge computing on Mars. Finally, I will conclude. So let us start with a little background info. In this animation of NASA, we can see the Mars Relay Network, which is made up out of 5 satellites. Their task is to serve as a communication bridge between Earth and Mars. So when this picture of the Mars rover Perseverance is taken on Mars' surface, it is first sent to one of the satellites of the Mars Relay Network. Then the satellites send the pictures to Earth. Now we can see it. Our first key concern is resource limitation. Due to the fact that computational resources in space are highly limited, rovers normally do not communicate directly with Earth. Our second concern here is the distance between Mars and Earth. Due to it, it can take up to 22 minutes for one signal to be transmitted between both two planets. This time is called round trip time, short RTT. So we have no live updates from Mars. This delay makes real-time operations, such as controlling rovers or analyzing critical data, impossible. As Mars becomes the next frontier, there will be a growing need for local computing resources. For example, for human habitats, autonomous rovers, or scientific probes. As the RTT for a signal is quite long, the computational infrastructure cannot be provided from Earth. Relying solely on Earth-based systems would be impractical. This is where edge computing, the integration of computational resources directly in Mars satellites, comes into play. By processing data on Mars itself, edge computing ensures that critical decisions can be made immediately. For example, this allows autonomous rovers to navigate without waiting for instructions, or scientific probes can analyze and pre-process data on-site before sending it to Earth. This could revolutionize how operations on Mars are conducted, making real-time collaboration and data analysis possible. There are multiple possibilities to provide edge computing on Mars. Today, I want to focus on integrating computational resources in satellites. For this, satellites in Mars orbit are necessary. Two possible types of satellite constellation can provide edge computing on Mars. On the one side, there is an aerostationary constellation, and on the other side, there is a low Mars orbit constellation. First, to the aerostationary constellation. Only 4 satellites will be enough to cover the whole equatorial circumference of Mars, which is marked here in a light orange. For this, we assume that we have a 53-degree minimum angle of elevation for ground station equipment. These satellites must be in an altitude of 7,000 kilometers above Mars' surface. Because of this altitude, we have a 10-watt requirement for a reliable 1 kilobit per second connection. Also, our round trip time would be about 125 milliseconds in such a constellation. Another option is a low Mars orbit constellation. In a simulation of Tobias Pfannzelter and David Bernbach of TU Berlin, they are using a Walker Star constellation. The Walker Star constellation is a satellite formation that ensures global coverage by positioning satellites in multiple orbital planes. As we can see on the left picture here, This ensures no blind spot for communication. The Walker Star constellation, like the Earth's Iridium network, allows satellites to maintain continuous coverage across the planet. In their simulation, they are using 9 orbital planes, marked here in green, with 9 satellites each, marked here in blue. So in total we have 81 satellites. The satellites would be at an altitude of 1000 kilometers above Mars' surface, and for 1 kilobyte per second connection, the ground equipment would require only 100 milliwatt. In this case, our round-trip time has a maximum of 12.5 milliseconds. This network would cover the whole of Mars, and the connection would be sufficient for most applications. While the described satellites constellation offer promising solutions for edge computing on Mars, environmental challenges unique to Mars and space must be addressed. For instance, satellites must withstand high radiation exposure, extreme temperature variations, and operate efficiently during planet-wide dust storms. These factors necessitate innovative designs for hardware, including radiation-hardened component, robust cooling systems, and dust-resistant solar panels. As we can see, the aerostationary constellation covers the basic with a minimum of satellites. In the long run, there would be more advantages with low orbit constellation, greater cover area, lower latency, and lower power consumption for connections between Mars surface and Mars satellites. Next, I want to point out the advantages of integrating edge computing into Mars satellites. If we want to connect two places on a planet into a network, there's more than one possibility. One, as we can see here, is to use a physical cable. Similar, there are physical cables on Earth to connect countries and continents. But another option is to use optical ISL, which stands for Inter-Satellite Links. With this technique, there would be a high-speed bandwidth at locations distance to ground station, unlike the need of physical cable. This technology is already used here at Earth. SpaceX satellites use it to connect distant locations without the need of a physical cable. Edge computing on Mars would provide a low-latency network for bandwidth-intensive applications. In this picture, we can see a rover on Mars, which is collecting data. Now, a simple way to make the data accessible to the people on Mars is to send all raw data from the rover to the habitat. But instead, with edge computing, the data could be pre-processed. This approach reduces the transferred data in the network. So, edge computing on Mars could help to provide a low-latency network on Mars. Also, edge computing on Mars could help reduce computational intensive tasks from low-power devices like rovers or scientific probes. As a concrete example, we can think of a rover which wouldn't have the necessity to compute the route, but instead could outsource the navigation to satellites. Due to the low latency, multi-party collaboration could be possible. For example, a user on Mars could remotely control a robot with a video live stream from the robot. Due to the low latency, this would not only be possible with one robot, but with many. With computational resources, data from Earth could be cached and outgoing data to Earth could be pre-processed. So here we can see that a rover, which collects scientific data, wants to transmit the collected data back to Earth. Again, we could just transmit all raw data. But instead, it reduces bandwidth to only transmit the pre-processed data back to Earth. The same is with incoming data. Instead of transmitting the same data from Earth again and again, with edge computing, these data can be cached. This helps reduce the bandwidth between Mars and Earth for high-priority tasks like emergency communication. And in general, edge computing on Mars would help reducing costs. The actual cost delta between providing edge computing from Mars surface and Mars low orbit is in the landing equipment. Without the necessity to land the servers, a lot of weight like back shield, heat shield, descent stage or propellant could be saved. An example, for the Mars rover Perseverance, the back shell weighed about 575 kilograms, the heat shield 440 kilograms, 640 kilograms for the descent stage, and an additional 400 kilograms for the propellant. In summary, about 2 tons. Compared to this, the rover itself weighs only about 1 ton. By just leaving the computational resources in orbit, there is no necessity for the entry, descent, and landing equipment. Now we have heard a lot of good arguments for edge computing on Mars. But what is the status of such? While Mars-specific satellite constellations for edge computing are not yet in the planning stage, there are similar Earth-based projects. For instance, Space Compass, a joint venture in Japan, is collaborating with Microsoft to demonstrate onboard space edge computing. This project aims to alleviate bandwidth problems by processing data directly on board, rather than transmitting all raw data back to Earth. Leveraging advanced edge computing technologies, it promises applications in Earth observation and disaster management. Similarly, Loft Orbital partners with the US Space Force to deploy modular satellites equipped for space-based data processing. Using flexible, commercial off-the-shelf hardware, their own YAM satellite buses exemplify scalability and innovation. This approach significantly reduces dependency on Earth infrastructure and could inform the design of autonomous systems for Mars missions. Both projects set the groundwork for future interplanetary networks, demonstrating how edge computing can reduce cost, enhance data processing efficiency, and support real-time operations in space. But even if there are no projects to introduce space edge computing on Mars, yet there are alternative ideas to provide real-time computing of large data. The first project is the creation of new chips. 2.5 years ago, in 2022, NASA chose the company Microchip Technology Incorporation to develop a high-performance space-thread computing processor, short HPSC. This processor should provide at least 100 times the computational capacity of current space-thread computers. HPSC processors are designed to address the challenges of space. These chips must be radiation hardened and energy efficient. The second project is the neuromorphic computing, which represents a breakthrough in energy efficient data processing. These chips simulate the structure and functions of the human brain, enabling them to process data much faster and with less energy consumption. In the context of Mars, these chips could be particularly valuable for tasks like autonomous navigation or real-time data analysis. For example, a rover could use a neuromorphic processor to make decisions on the fly, such as avoiding obstacles or analyzing terrain, without relying on distant Earth-based systems. As NASA's 2022 flight of a neuromorphic processor showed, these chips have the potential to revolutionize how we approach remote operations in extreme environments like Mars, where computational power and energy efficiency are key concerns. The chip was in the satellite, which we can see in this picture here. Now that we've come to an end, I would like to give you a quick conclusion. The challenges which were described in the beginning of the presentation, long communication delays and resource limitation, can be overcome by space edge computing. Hence, edge computing will play a pivotal role in the future of Mars. The integration of computational resources directly within Mars orbit or on satellites not only offers a solution for real-time data processing, but also enables autonomous navigation for rovers, more efficient data management, and cost-effective mission operations. Also, Mars colonization is still years away. The groundwork for a Mars cloud capable of providing low latency, high-speed computing through orbital satellites is already being laid. There are already projects on Earth which illustrate the feasibility of such technologies in space. Moreover, advancements in neuromorphic processor and high-performance space-thread computing signal that the necessary computational power for future mission is not far off. In the grander scheme, edge computing on Mars will not only support exploration, but also pave the way for future missions on other planets such as the Moon or Venus. By leveraging orbital computational resources, we can build a sustainable, autonomous, and efficient network on Mars. Thank you very much for your attention. In the description below you can find the underlying resources.